Hello everyone, it's 1 p.m. Eastern and that means it's time to begin our second CoCoRaHS Weather Talk webinar of 2017. Thanks for joining us today. I'm your host Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from the Colorado Climate Center at Colorado State University here in Fort Collins, Colorado on an unseasonably warm first day of spring. Shouldn't we be seeing snowflakes out there this time of year? Well, not today. We'll be recording today's broadcast for future viewing. In fact, all of our 56 past webinars are viewable via the CoCoRaHS Weather Talk website. Finally, all of our Weather Talk webinars are sponsored by the generous donations of listeners like you, and we thank you very much for that. Well, we hear the word carbon used a lot in the news these days, but what is it? How does it affect the atmosphere and our planet? Where does this carbon go? Well, these are questions many have been asking these days, and today's webinar will take a look at this very subject, and I think you'll be fascinated about what we're about to find out. With us today is Scott Denning, a longtime friend of CoCoRaHS and actually our next-door neighbor here at the Colorado Climate Center. Scott is a Mofford Professor of Atmospheric Science at Colorado State University. Scott leads a big group of graduate students and scientists who study the global carbon cycle using data collected all over the world and from satellites. It's been his life's work to try to map out the uptake of atmospheric CO2 by plants and soils on land. Originally from Maine, Scott has lived in Fort Collins since the 1970s. He and his wife have 2 grown sons, 2 cats, and a Labrador Retriever. On most clear, moonless nights, Scott can be found at a mountain cabin near Timberline, not too far from here, where he takes long-term exposure photographs of distant galaxies and nebulas. Wow, that's fascinating. Well, Scott, welcome. It's great to have you on our broadcast today. Hey, I've got a question for you. You've done a lot with astronomy. How did you get into atmospheric science, and did you always know you were going to study weather?
Well, hi, Henry. Yeah, when I was in the 2nd grade, I learned about planets and stars and decided I wanted to be an astronomer when I grew up. That was in the Apollo era, and I, like many of my other kids in class, was just captivated by those moon launches and even moon landings that we saw in school on these, rolling TV things that they'd roll into class every few months. Later, when I went to college, I found out there was no such thing as an undergraduate astronomy major. You had to major in physics or math or something. And after I went hiking in the Grand Canyon, I decided I'd study geology instead. After college, I worked for a while in the oil industry. Industry collapsed in the mid-'80s when the price of oil fell by 2/3, and I lost my job and was looking around for something to do, and actually wound up in graduate school in the late 80s studying atmospheric science. And the atmosphere is a perfect place for me to study because the sky is right there in the middle between the rocks underneath us and the cosmos out beyond. So I love my career on weather and climate, but at night I still get to do the astronomy stuff as a hobby.
Well, that's great, and it would be neat to someday see some of your photographs. It sounds pretty exciting to actually get those shots from so far away. Wow.
Cool. Well, I'll send you a link for that.
Okay, that's great. Well, Scott, take it away. The webinar is yours, and we'll have questions coming up at the end. And so, folks, sit back and enjoy what should be a really interesting webinar today. Thanks, Scott.
So thanks a lot, everybody, for joining in. I'm going to talk today about carbon, and I guess the short version of this is everybody's heard about burning coal, oil, and gas, adding to the CO2 in the atmosphere, but most people haven't really thought very much about where does that carbon go. So the short version of this is, where has all the carbon gone? A long time passing, and I'm going to try to answer that question today. What is carbon? Carbon is an element. Carbon is the 6th element in the periodic table. It's got 6 protons and 6 neutrons, therefore 6 electrons. All of the carbon in the universe, of course, was made in the inside of stars. You smack 2 hydrogen atoms together inside a star to make a helium, and you take 3 helium atoms and you smack those together and it makes a carbon atom, and that's where all the carbon in the universe comes from. It's actually quite common in the universe because of that. Carbon is super important to everything, to chemistry, because carbon has 6 electrons. The outer shell of every carbon atom has 4 valence electrons, and that makes it really easy to react with stuff. It can either donate up to 4 electrons, or it can receive 4 electrons to complete its shell, and that sort of super duper plug and play ability of carbon makes it the basis for all of organic chemistry, and therefore all of biochemistry, and therefore all of life. So all proteins, all DNA, all the chemical reactions that underlie biology from the molecular scale all the way up through plants and animals to the global biosphere, are all based on the chemistry of this incredibly versatile chainable carbon atom. So probably everybody's heard of photosynthesis. It's actually quite an incredible thing, and we're very, very lucky that plants, about halfway through the life of the Earth, so a couple of billion years ago, developed the ability to turn inorganic CO2 molecules into living juice, living material. This is a really remarkable thing. Just CO2 is kind of the ashes of the carbon cycle. It's the completely spent, thermodynamically used up, fully reacted carbon, where each of those 4 potential bonds is already used up by an oxygen, inorganic gas in the air, but plants drive that carbon up a thermodynamic gradient and make long-chain molecules that store energy by taking sunlight, and just like a photovoltaic cell, they capture some of that sunlight and they store that energy in long-chain carbon bonds to make organic molecules that wind up getting strung together into bigger and bigger organic stuff that is basically the base of the entire food chain. That carbon is then stored energy is then released through respiration. So, obviously if we could photosynthesize, we wouldn't have to go to work. We could just lay out in the sun and get fat. Plants are able to do this. Animals are not. We have to eat the plants, or we have to eat something that ate the plants, and that's where we get our energy. And then when we respire energy, when we burn energy in our bodies, of course we blow that carbon back out into the air as CO2. And it's not just us that do that, it's actually bacteria and microbes that do that. So virtually all of the carbon that gets fixed through photosynthesis winds up getting released through respiration. That carbon is mostly released by respiration, but a tiny, tiny amount of it doesn't get released by respiration, because some of that carbon winds up getting buried in the mud as dead material, and if it's buried quickly enough in the mud, it's out of range of the bacteria. There's no air, there's nothing to allow the bacteria to get a hold of it, and it's physically isolated in the mud and becomes preserved as fossil remains, literally fossils in the muck at the bottom of the sea or the bottom of a lake. Over really long periods of time, that fossilized muck gets hot and undergoes chemical reactions and turns into hydrocarbons, turns into oil and gas and coal. And over even longer periods of time, that oil or gas is lighter than water, just like salad oil or salad dressing will separate into water and oil, and the oil floats on the water. So up comes the oil until it hits a layer of rock that's impermeable, and eventually if the rocks fold, this sort of impermeable layer will trap some of the oil and gas in the upper parts of these folds, and along come millions and millions of years later guys in pickup trucks like I was when I was right out of college, and we drill 7-inch wide holes down into the rock, sometimes thousands of feet down, to hit this oil and gas deposits, and most of the time we miss, but about 10% of the time we find oil, and of course that's what we use to run our global industrial civilization. So here's a sort of typical organic molecule, a hydrocarbon molecule. This one's got 1, 2, 3, 4, 5, 6, 7, 8 carbons, so it's an octane. Each carbon has a carbon-to-carbon bond and then also hydrogen bonds, and that hydrocarbon is then reacted with oxygen, so we set it on fire, and out comes the energy that was stored in these carbon-to-carbon bonds. Where did that energy come from? That's the solar energy that was trapped by photosynthesis millions of years ago in those algae or you know, whatever little critters in the water, buried in the rocks, turned into hydrocarbons. Pow! Out it comes, and that stored energy is then used to power all of civilization. On the other hand, every carbon gets reacted with 2 oxygens, comes out as CO2. Every hydrogen goes with a buddy and reacts with an oxygen, so it makes an H2O. So a perfect combustion of this octane would yield a bunch of CO2 and a bunch of oxygen, water vapor, and a bunch of energy and nothing else. But that's the basis of carbon and energy and the world economy. It's actually been understood almost for 200 years that solar heat alone is not enough to explain Earth's warm climate. This fellow, Joseph Fourier, back in the 1820s, nearly 200 years ago, showed that quantitatively and coined the idea of a greenhouse effect, greenhouse analogy, where sunshine comes in but the heat can't get back out, just like a greenhouse. A few decades later, John Tyndall made the first direct laboratory measurements of the absorption of infrared radiation by CO2 gas in his laboratory. It was during the U.S. Civil War when Abraham Lincoln was president. He showed that CO2 absorbs that IR radiation smack in the middle of the wavelengths that are emitted by the Earth, and basically explained the relationship between CO2 and climate by direct laboratory measurement. 120 years ago, Svante Arrhenius, a Swedish scientist, physicist, actually measured this infrared absorption in the Earth's atmosphere, in the outdoors, and proved through these years of measurements that doubling CO2 would warm the global climate, global average temperature by 3 degrees Celsius. So this is a number that goes back to, you know, my great-grandparents' time. In the 1930s, this fellow Guy Callender made low-precision CO2 measurements. They didn't have really good instruments, but he measured CO2 all over the world, and it looked like it might be increasing. Previous to that, everybody thought the extra CO2 from fossil fuels would just dissolve into the oceans and wouldn't contribute too much extra heat to the Earth. But Callender suggested that the CO2 from coal might not be dissolving into the oceans, might actually be accumulating in the atmosphere, and therefore would lead to climate change. That was back during the Great Depression, run up to World War II. In the post-war period, Dave Keeling, a scientist in Southern California, finally developed an instrument that could successfully, precisely measure the CO2 in the atmosphere. It was the first time we had really good measurements of CO2 in the atmosphere. It was before I was born. He made these measurements in 57, and by 59, had installed instrumentation at the top of a volcano in Hawaii, Mauna Loa, almost 14,000 feet above sea level in the middle of the Pacific, as far from industry as you could get. And we've had hourly measurements of CO2 from the top of that mountain ever since. Dave Keeling died in 2005, and he was an amazing scientist. So starting in the 1960s, based on Keeling's measurements, this is the top of Mauna Loa where those measurements began about 60 years ago. The measurements showed that CO2 was actually rising pretty fast, not dissolving into the oceans as people had previously expected. Maybe more importantly, Keeling showed very quickly that the increase in CO2 in the atmosphere was only half as fast as the production of CO2 by burning coal, oil, and gas. We know how much coal, oil, and gas is burned because, of course, for commercial reasons, people who dig up coal, oil, and gas count how much stuff they produce, right? Exxon has to report their production to their stockholders, so they know very accurately how much they produce, and you can tote that all up. And it turns out that the CO2 in the atmosphere is rising only half as fast as the production of CO2 by burning all that fuel. So in other words, half of the fossil fuel carbon is missing. It's not in the air. And this was known by the middle of the 1960s, and it was kind of a mystery. Where's the rest of the carbon going? So the first thought was, well, it's dissolving into the oceans. That's what everybody had previously thought was happening to the carbon. Anyway, carbon dissolves in water by making carbonic acid, and carbonic acid is basically just carbonate, right? Carbonation, the process that makes soda or beer or wine fizzy is just the creation of an acidic molecule in water, and you know, that's kind of why we drink beer with pizza or Chardonnay with brie. It's got that nice kind of bracing bite on your tongue. You can feel the bubbles tickling your tongue, and so that's carbonic acid. It goes good with cheese. On the other hand, we also know that CO2 dissolves twice as well in cold water as it does in warm water, and that's of course why beer and soda go flat when they warm up. If you leave a beer out on the kitchen table too long, it'll warm up and the CO2 will degas. And the oceans work just like that too. Cold polar ocean water soaks up loads of CO2 because it's cold. And then the warm tropical oceans, the water comes to the surface, warms up in the sun, and it goes flat, just like leaving the beer out on the table. So the CO2 goes into the oceans at the poles, and it comes out of the oceans in the tropics. If you care, this is the full-blown chemistry. You see CO2 reacting with H2O into water. That makes this carbonic acid, H2CO3. The carbonic acid dissociates to make a hydrogen atom over here. And a bicarbonate atom. Something like 90% of the carbon in the ocean is bicarbonate. And then the bicarbonate also can dissociate to make another hydrogen atom. So you can see these hydrogen atoms, that actually changes the pH of the ocean. So dissolving CO2 creates hydrogen atoms, ions in solution. So dissolving CO2 actually acidifies the ocean. The other thing it does is interacts with the carbonate. Carbonate is the key ingredient in seashells, so changing the CO2 dissolved in the ocean changes the solubility of seashells in the ocean. Very, very important. In the long run, we'll return to that at the end of the talk. So yes, there's a nuclear blast on this slide. I don't mean to scare you, but it turns out that nuclear weapons figure prominently in the early 60s as part of the carbon story. Basically, before 1963, the U.S. and the Soviet Union used to blow off nuclear bombs in the atmosphere. This is kind of a terrible thing. But in 63, they signed a treaty that said they would not do that anymore. They promised to never blow off any more nukes in the atmosphere. And so right before the treaty went into effect, they blew off dozens of these things in the atmosphere, quick, before it was too late, and that created a giant spike of radioactive CO2 in the atmosphere in 64, and the CO2 that was produced by this bomb spike of bomb tests has the same chemistry and biology as regular CO2, but it's got this sort of radioactive label that says, I was made in 1964 during this giant spike in the bomb test. So it's like a special labeled CO2, and oceanographers were able to go out and actually find that 1964 CO2 in the oceans, and so they were able to work out the rate at which CO2 can be taken up by the oceans because they had this slug of labeled CO2 that was made by the bomb testing in 1964, right before the treaty went into effect. And so they were the ones that discovered that only half of the missing carbon, so we know that half the CO2 is missing because the rate of CO2 in the atmosphere only goes up half as fast as the burning of the fossil fuel, and we know that that half of the missing carbon is in the oceans. So that leads to the idea of a missing sink. If you think about fossil fuel burning, that's the total amount that we burn, and we know that from commercial records. You know, you tote up all the coal and all the gas and all the oil that's burned in a year, let's call that 100%, and then we can measure the amount of CO2 that increases in the atmosphere from year to year, because we got these hourly measurements from the top of Mauna Loa, and then later we had measurements from all over the world, and it's actually pretty easy to measure the rate at which CO2 increases in the atmosphere, so that's a straight up measurement. You got an ocean uptake of CO2, and we can measure that by calculating the rate of increase of CO2 in the ocean from this big spike of radiation labeled CO2 in 1964 that came from the bomb testing. So you add the CO2 from fossil fuel burning, you subtract the increase in the atmosphere, you subtract the uptake by the ocean, and that gives you this missing sink. So there's this residual of about a quarter of the fossil fuel emissions. You got fossil fuel burning minus the part that goes into the atmosphere minus the part that goes into the ocean, gives you this missing 25%. So oceanographers said, well, there's missing carbon, must be on the land, right? Maybe it's just the plants reacting to the extra CO2. Kind of makes sense, right? Plants eat CO2 for a living. We call that photosynthesis. Maybe adding the CO2 to the air makes the plants bulk up. It's kind of the Girl Scout cookies theory of carbon cycle, right? It's like adding CO2 to the air is like adding Girl Scout cookies to my house. I bulk up if there's more Girl Scout cookies in the kitchen cabinet. Actually turns out in the laboratory and in greenhouses, it's definitely true that adding CO2 does make plants grow faster. This is an example where you got rice plants grown in a greenhouse, and you give them a little bit of CO2, a little bit more CO2, a little bit more CO2, and as you ramp up the CO2 to very high levels like 800 ppm, they grow faster. It's the same plants grow faster the more CO2 you give them. So there's no question that they do eat more if you give them more food, but it turns out that doesn't necessarily explain why there's a missing sink. And that's a little bit complicated, but bear with me here. This is kind of an important point, that just adding plant food to the atmosphere doesn't necessarily mean that, that CO2 gets sucked out of the air, because not only do plants grow, but plants die. You know, all things must pass. I'm sort of reminded of Arya Stark in Game of Thrones, you know, all men must die, or all plants must die. Everything dies, and everything eventually is eaten by the microbes, and those microbes eat up all the carbon, and 100% of that carbon gets respired back to CO2. I'm also reminded of the Lion King, right? Mufasa says, you know, we eat the antelopes, but in the end, we become the grass, and you know, it's the circle of life. Well, the lions, you may think of them as the top of the food chain, but actually the microbes are the top of the food chain. They wind up eating even the lions. So all of the plant material that is fixed by photosynthesis winds up getting turned back into CO2 with enough time. We know that for centuries, even millennia, before the Industrial Revolution, this graph shows measurements of CO2 in the atmosphere back to the year 1000. Those are from ice cores in Antarctica. And so you can see that the CO2 was almost dead steady for centuries, actually for millennia, for thousands of years before the Industrial Revolution. The CO2 was almost dead on, 280 parts per million in the atmosphere, and only in about 1800 did it start going up, and of course now it's been going up like crazy in the more recent years. But the reason why it didn't go up and down very much, it only went up and down like just a couple of ppm over thousands of years before the Industrial Revolution is that growth and death were balanced over this very, very long period of time. The amount of plant growth was balanced by the amount of plant death and then decomposition. So that was a balance, but what we're saying now is that the balance is over, that we have an imbalance. When we say that there's a carbon sink on land, believe it or not, we're saying that over many decades that we've been making these measurements, plants are growing faster than they're dying. It's not just that they're growing, they've always been growing. The difference when we've got a land sink means that plants are growing faster than they're dying. It's not true everywhere. Like it's not necessarily true in my backyard. If my dog is digging up the garden, then they're dying faster than they're growing. But taken together over the whole earth, the plants are growing faster than they're dying. Since we've started having good measurements back in the 1950s, the total amount of plant growth minus the total amount of plant decay has been about 25% of fossil fuel combustion. A quarter of the fossil fuel combustion gets taken up as a net by growth minus death of the plants. Really amazing. Now, how can it be possible that plants are growing faster than they're dying? Don't you know about tropical deforestation? You know, what about clearing land in you know, my neck of the woods? We're bulldozing plants and building subdivisions. What about plowing the prairies and planting crops? Aren't we digging carbon out of the soil? Pave paradise and put up a parking lot? You'd think that the total amount of plants on the earth was shrinking, not growing, but it actually turns out it's growing. How is this possible? How does it work? So if you think about the sort of flow of CO2, it starts out in the atmosphere. There's this net plant production to make plants. Plants die. Some of that dead plant material goes out, gets eaten by, like, think about the leaves that fall off your trees. They get eaten by bacteria, whatever. Some of that goes out to CO2. The rest of it turns into litter on the forest floor. The litter gets eaten by other microbes, and some of that gets breathed out by the microbes, turned into CO2. The rest of it gets pooped out, like microbe poop, becomes soil carbon. The soil carbon eventually also gets eaten by microbes, and that gets blasted out by CO2 in the long run. So all of the carbon that goes in as plants eventually kind of gets leaked out of the carbon cycle by microbes and returned to the carbon, but to the atmosphere. But some of it actually resides in these storage pools as litter, you know, live plants or dead plants or soil carbon for a long, long time. And so if you increase the growth of the plants, eventually all that's going to come out, but some of it's going to stay in these pools for a while, and that's what makes it a sink. So if you sort of imagine the growth and the decomposition total in the world over time, if this is 1850 and, you know, here's the year 2000, the net plant production increases over that time because the CO2 is rising, so the photosynthesis is rising, and the total amount of growth is going up, but the total amount of respiration goes up as there's more stuff to eat, but there's a time lag. This little tau or time lag is the average length of time that the CO2 stays in the atmosphere. So like I said, in my backyard it might only be a week, because that's how long it takes till I mow the lawn. But on the other hand, like in redwood trees, it might be thousand years or something like that. And the average over the whole world might be like 10 or 20 years. So the average residence time of carbon in the land ecosystems is decades. So there's a difference between the rate of increase of plant growth and the rate of increase of plant death, and that difference in any given year is a carbon sink, right? The difference between growth and decay in a particular year is some total amount of carbon, and that's uptake, net uptake. And if you sort of subtract this in different places, you expect that the tropics, so this is latitude here, the tropics are a good place to make carbon sink because there's lots and lots of plant growth there. But on the other hand, so is the boreal forest, because there's a longer residence time up there. The soils are cold. It takes a long time for the carbon to come back out. So different places have different amounts of fertilization sink. So increasing plant growth then gets delayed by the plant, carbon stays in the plants because the respiration is behind by this residence time. So people have actually gone out and measured this, believe it or not. We have this technology called free air carbon enrichment. It's FACE. They actually fumigate real forests and other ecosystems in the outdoors by building these rings of towers, and you spew CO2 out into the air, and it changes depending on the wind speed and the wind direction, and you keep the outdoor CO2 over these rings at an elevated level, at different elevated levels over time. It's very expensive, very labor intensive, but you can actually do these controlled experiments, replicated treatments, and measure the effect of CO2 on plant growth and plant decomposition over decades. And the results from these giant experiments over time have shown that, yeah, you get a bump in plant growth in elevated CO2 compared to the ambient CO2. So the high CO2 rings of trees grow faster, but after a bunch of years, they slow down until they're pretty much the same. So the net increase in the wood in these plants is greater for a while, and then it sort of tails down to being near zero after a bunch of years. But then after maybe say 5 years, when it tails off and you don't get any extra enhanced growth anymore, if you juice them up with extra nitrogen, then they grow faster again. So it seems like the amount of nutrients in the soil limits, like most plants, they can take some extra CO2 because it's extra food and make extra plants, but eventually they run out of something else. They're not just starving for CO2. They for every bit of CO2, they also need some nitrogen, some water, need some light. So other nutrients come into play as limits to growth. Turns out we've been taking care of that limit as well. Since the beginning of the 20th century, humans have been fixing nitrogen. Most nitrogen is actually not bioavailable. It's triply bound nitrogen, N2, in the atmosphere, chemically and biologically inert. And the only nitrogen in the biosphere, like proteins and all that, used to come from lightning. Lightning bolts blast the atmosphere, allow the N and the O to react with each other. It burns some of the nitrogen in the atmosphere, and that naturally fixed nitrogen is the nutrient cycle for all of the biosphere. But humans figured out in the early 20th century through the Haber-Bosch process how to burn our own air, and we've been making nitrogen fertilizer ever since. That led to the Green Revolution. In fact, since about 1980, human fertilizer production has exceeded the total amount of nitrogen fixed by lightning in the atmosphere, and we use that fertilizer to grow our food. It's not just fertilizer, it's also from combustion. When we have industrial combustion or combustion in our internal combustion engines, we actually burn some air in our engines that's reacting the nitrogen and the oxygen to make nitrogen oxides. That winds up oxidizing to nitrate in the clouds. Comes down like Miracle-Gro in the rain, and it blows downwind in these little plumes that come out over the downwind of the industrialized parts of the world. Many forests in those parts of the world that happen to be downwind of these industrial combustion emissions wind up being almost 200 times as much carbon as nitrogen in those forests, and since they're nitrogen limited, they take up 200 kilograms of carbon for every 1 kilogram of nitrogen we put on them through this massive nitrogen deposition. So it's not just carbon we've added to the climate or to the biosphere, it's also nitrogen. But wait, there's more. When I was a kid, we used to go out in the woods and we would find, I grew up in New England, and these beautiful closed canopy forests in Massachusetts and Maine, and out in the middle of the woods you'd find these amazingly well-constructed stone walls that are growing moss that have been there for decades under the trees. Why did somebody go to the trouble to build a stone wall out in the middle of the woods? What were they thinking? Well, it turns out that it didn't used to be woods. There was no forest at all in New England 150 years ago. These were all pastures and farms, and so this was the boundary of somebody's pasture. But over the 20th century, family farms basically shut down in New England as farming moved to the Midwest, and as the production of fertilizer allowed sort of giant agribusiness to take over, and all those people had to move into town and get a job in an office or a factory or whatever. and they let their woodlands and forests regrow. And every molecule of wood in these regrowing forests in the developed world was derived from atmospheric CO2. So this is a net storage of carbon in the plants because you've got trees that are growing where there didn't used to be trees. You sort of imagine going from an old field to a forest. Over time, the growth is exceeding the amount of rotting dead wood, and so though carbon is accumulating and accumulating and accumulating in that forest, eventually the rate of death catches up with the rate of growth, and you wind up getting a sort of flatlining of the amount of storage. The young forests accumulate carbon, but old forests are sort of it's steady state. They're no longer accumulating. You sort of imagine as the years go by, the growth rate is really fast at first, and it kind of tails off. The respiration rate is delayed until you got enough forest litter and dead stuff at the bottom of the woods and in the soil to catch up with the photosynthesis. So all this growth of new forests is a big deal. The last one I want to talk about real quick is boreal warming. It actually turns out the Arctic is warming twice as fast as the world as a whole. For various reasons, the Arctic is by far the fastest warming part of the world, and even south of the Arctic into the boreal forest, a lot of places have half again as many frost-free days per year as they did 50 years ago. And this is actually from satellite data. We detect a change in the rate of plant growth up in that warming part of the far north, and a lot of this is driven by the warming itself. You see the forest moving north, the northern tree line, into the tundra. You see shrubs invading the tundra and forest growing further and further north, and that's again storing a lot of carbon in the ground as the tree line marches up into the Arctic due to warming being so fast up in the Arctic. So I want to talk for a second about units of measure. I'm going to talk about gigatons of carbon, like gigabytes in your hard drive are billions of bytes. A gigaton is a billion tons of carbon. A gigaton is precisely the mass of 1 cubic kilometer of water. If you have a cube that's 0.6 of a mile wide by 0.6 of a mile long by 0.6 of a mile deep, this is going to be precisely 1 billion tons, 1 gigaton of carbon. By the way, that's 3.7 gigatons of CO2 because you got to increase for the weight of the oxygen in that gigaton. But a gigaton of carbon is a big bunch of carbon. There's 800 gigatons currently in the atmosphere. This shows the 3 big pools. There's the ocean, the atmosphere, and the land. 38,000 gigatons of carbon dissolved as bicarbonate ion in the oceans. Only 800 in the atmosphere, about 2,000 gigatons in the land. Human beings dig up 10 gigatons of carbon a year out of the rocks. That's our fossil fuel. We set it on fire, put it into the atmosphere. So this 800 gigatons in the atmosphere is being increased by mining the carbon, putting it up there, but only half of it shows up. This 10 gigatons is put in, 5 gigatons shows up, but that 5 gigatons is less than the 10 we put in. The other 5 is distributed between the land and the ocean. There's these ginormous one-way trips of carbon, about 120 gigatons into the land, 120 gigatons back out. 90 gigatons dissolves into the oceans, 90 gigatons back out. But these missing gigatons, 5 missing gigatons, is kind of hard to find among these giant natural cycles of carbon. This huge amount of carbon goes in and out of the land from photosynthesis and death, and a huge amount of carbon goes in and out of the ocean as well. I'm going to skip some of that. Talk again a little bit about the ocean side of this. The oceans are not well mixed. The oceans are stratified thermally. So this shows the oceans almost like a bathtub. Here's the South Pole. Here's the equator. Here's the North Pole. The ocean surface down to the deep part of the ocean, 4 kilometers, 13,000 feet average ocean depth. And almost the entire volume of the ocean is very, very cold. only about 3 degrees Celsius, about 38 degrees, 39 degrees Fahrenheit. Even in the deep tropics, the deep ocean is super cold. Only the surface water is warm because the sun beats down on the surface, makes it warm, but the surface warm water is buoyant like a cork. It floats on top of the deep cold water because it's warm and it's less dense, and it seals off the deep ocean so that it doesn't touch the atmosphere. The only way the water that touches the atmosphere can get down into the deep water is here in the far north. We call that North Atlantic deep water. It gets super cold in like Greenland in January, and that water's colder than the water at depth, and it sinks. Also the Antarctic, around Antarctica, it gets colder in July than the deep water. We call that Antarctic bottom water, and that water takes about 1,000 years to fill up the bottom of the ocean, kind of push up the rest of the water. The rest of this water that's not touching the atmosphere is in the cold, inky black Davy Jones locker. Doesn't know we're here yet, has no CO2 dissolved in it from fossil fuels, has none of that bomb radiocarbon in it. So that's what limits the rate. We've actually observed that carbon in the deep ocean by sailing ships all over the place and dropping these little flasks to the bottom of the ocean. Every one of these little dots is a place where we've measured the CO2 in the ocean all the way to the bottom. There's thousands of these little dots where people actually went out and sampled the CO2 all the way to the bottom. And what we find is here's the Atlantic, here's the Indian Ocean, here's the Pacific, and all different latitudes. And you see that the fossil fuel CO2 is only dissolved into the top parts of these oceans, and very, very little of it has penetrated to the deep ocean because it's thermally stratified. It's stuck in the top of the ocean. So it's hard to get the fossil fuel CO2 to get down into the ocean. The other important thing about putting CO2 into the ocean is it reacts with the ocean to make carbonic acid, right? Just like fizzy water, just like that bubbly water that goes good with cheese. Putting CO2 into the oceans makes acidic oceans, and that changes the pH of the oceans. It changes the solubility of carbonate of seashells in the ocean. It fundamentally makes the oceans less able to take up the CO2, and it causes substantial changes in the biology of the oceans, the chemistry of the oceans. If you put enough CO2 into the oceans, it's got incredibly bad long-term consequences for ocean life. So where has all the carbon gone? Remember that there's exchanges between the ocean and the atmosphere and the land. We put fossil fuel into the atmosphere. Some of it goes into the oceans because it dissolves. Other parts go into the ocean because it gets taken up by like algae and stuff, and there's this little rain of dead algae and dead muck down to the bottom of the sea. In the land, we talked about CO2 fertilization. The plants eat CO2. More CO2 is better. They make more plants. We got nutrients. We add a lot of nitrogen to the biology, and that deposits into the biology and fertilizes the plants, and they take up more CO2. We regrow forests in parts of the world like Massachusetts and Maine and Germany and Japan, and that sequesters CO2. And then there's also the warming of the Arctic and the boreal forest, and that allows the trees to encroach into the Arctic and suck up CO2. So about half of all the carbon has gone into these various sink processes. And let me talk about those sinks. So the trouble is that eventually all of those sinks will fill up. So you sort of think about a sink that's got some drains, but you're pouring water into it faster than it can drain out. On the land, the sinks are very vulnerable and very uncertain. Really only the CO2 fertilization part has legs. If you keep adding CO2 and the land is reacting to that extra CO2 by taking up more carbon, that's a good thing. That means the uptake of CO2 will probably increase as we increase the CO2. On the other hand, adding nitrogen, extra nitrogen beyond what the plants want, it just comes out the bottom. It's like if you put some Miracle-Gro on your tomatoes, they're going to grow faster, but if you put 10 times more Miracle-Gro, they're not going to grow 10 times as fast. They're actually probably going to die. So that doesn't help you. Regrowing forests are only taking up carbon until they're done regrowing. Then the rate of death equals the rate of growth again. So those are just transient sinks. Boreal warming is even worse because as you warm a little bit, maybe you advance into the tree line into the Arctic, but if you warm more, you're going to thaw the permafrost, and all this carbon that's stored in permafrost thaws out, comes back out into the atmosphere. That could actually switch the far north. Instead of being a sink, it could become a huge source. So land sinks are very uncertain for the future. Ocean sinks, probably safe for the near term, but even scarier for the long term, because in the long run, getting CO2 into the ocean is limited by this physical mixing against buoyancy. You got to take that warm water at the surface and make it sink to depth. As you warm the oceans, that mixing to the deep ocean slows down because you're making the surface warmer. It's more buoyant. It doesn't sink. Actually, it takes thousands of years for the oceans to circulate and to get rid of that CO2. Plus, in the really long run, thousands of years from now, the chemistry of acidification, making carbonic acid, will limit the total amount that you can sock away into Davy Jones' locker. So in the next 100 years or so, when we calculate the amount taken up by land, this is from 1850 out to 2100, a bunch of different calculations show that the land uptake might increase if CO2 fertilization drives things. On the other hand, it shows that some of these models predict the land's uptake will stop or slow down or even reverse if you start killing off the tropical forests or melting permafrost. Oceans probably take up CO2 more and more, but the amount varies a lot depending on how warm you make that surface ocean. So even for the same amount of CO2 in the atmosphere, you have quite a bit of uncertainty. Hundreds of ppm uncertainty in the amount of CO2 in the atmosphere. All depends on how those sinks on land work and how those sinks in the ocean work. If you think about the CO2 of the world, think about the atmosphere as being a big bathtub. We pour 10 billion tons a year, 10 gigatons a year into the bathtub from the faucet. The currently bathtub holds 800 billion tons of carbon, blah, 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 but that's going up each year by about 5 billion tons because 2.5 billion tons are going out each into the ocean and into the land. So there's these drains that are going out the bottom. Unfortunately, the warming comes from the water in the tub, not from the faucet. So we could turn down the faucet, but the level in the tub is still going up. But ultimately, those drains from the tub, they're not connected to the sewer, or at least not on any good timescales. The plants and soils soak up a lot of carbon, but there's only so much room for extra carbon in the plants and soils because of these saturating sinks. The deep ocean can hold quite a lot of carbon, but it's only going in there drip, drip, drip very slowly because of the slow mixing into the deep oceans. Eventually, it can go into sediments and rocks, like over geologic time. There's a huge reservoir there, but it goes in so slowly that it takes forever. You can sort of imagine, here's a time scale out to the year 40,000, right? So this is, nobody's predicting this. This is just sort of a cartoon, but you can imagine if we inject a huge injection of CO2 around the year 2000, some of that goes into the ocean over the next several thousand years. You maybe get by the year 10,000 or something, you've gotten rid of 3/4 of that carbon, but that is still thousands of years from now. Then it has to react with the calcium carbonate in the ocean, dissolving seashells, for tens of thousands of years, and maybe by the year 40,000 AD, you've got rid of 90% of the fossil fuel CO2, but some of that CO2 that we emit today will still be warming the climate 100,000 years from now because it's this very, very slow change. Anyway, in summary, the CO2 in the atmosphere cycles vigorously with huge pools of carbon in the land and the oceans. The growth and death of plants over the whole planet have mostly been perfectly balanced over geologic time. The amount of CO2 in the atmosphere has varied, but only super slowly as the plants, the more you grow them, the more dead ones there are for it to be decomposed by the bacteria. So there's been this long-term balance between growth and death that's allowed life to evolve over geologic time. Currently, we're mining this tiny, tiny residual between the growth of plants and the death of plants that's left a fossil residue in the rock reservoir over 500 million years. Took hundreds of millions of years for that oil and gas and coal to build up. We're mining it in just a few centuries, injecting it into the atmosphere. It reacts with the oceans. It reacts with the biosphere. Those reactions take up about 50% of that fossil fuel CO2, but the the accumulation of fossil CO2 in the land and ocean is sort of a mixed blessing because some of it will stop going into those reservoirs pretty quick, and some of it will take thousands of years to go into the oceans and eventually the rocks. So these carbon sinks will saturate over a long period of time, and unfortunately some of the CO2 that we emit, you know, today, tomorrow, 50 years from now, will still be in the Earth's atmosphere hundreds of centuries from now. So that's it for my presentation. These sort of hard to read links, please feel free to copy and paste those suckers into your browser. The first link lets you download the slides that you just saw. The second link is to a text article that I wrote that sort of explains the same information in words. Anybody's perfectly free to email me with questions or comments. My email is there, and also invite you to follow me on Twitter. I post various things about carbon and climate on here. As always, CoCoRaHS will have the links to the slides and the article and the email address and stuff on their website. And now I'd like to open it up for questions.
Thank you, Scott. Wow, what a fascinating presentation. I bet a lot of people would like to sign up for your class.
I actually teach a class on this stuff at CSU, and this summer, if anybody's in the area, I'm going to teach a 3-day class live here at CSU. I'll send you a link to that later.
Okay, great. Well, we really appreciate your time. This is fascinating stuff, and you know, boy, I remember living in New England, seeing those stone fences that you talked about and the trees, and wondering the same thing. Why are there trees growing there at this point? And,
yeah.
Very, very interesting things. Well, we're going to take some questions. We've got a bunch of them starting to come in right now. Actually, somebody was wondering, are those CSU classes available? Are they online? Would your class be online? For them
I don't have an online class. I'm trying to build one.
Okay.
Filming the lectures. Unfortunately, at this time I don't have it, but when I do, maybe CoCoRaHS can help me post a link to your
sure.
to your followers.
Love to do that. Well, here's a couple questions. Ann writes in, and she wants to know, has the increase in human population added to CO2 in the atmosphere?
So not directly. The people ourselves are not adding CO2 to the atmosphere in a meaningful way in terms of like literally our bodies, our respiration, because all of the CO2 that we respire of course, was taken out of the atmosphere to make the plants, and the animals ate the plants, and we ate the animals and plants, and then it goes back out as the CO2 that we breathe. So the increase in human population itself does nothing to the CO2 in the atmosphere. What's increased the CO2 in the atmosphere is the fact that all 7 billion of us are setting carbon on fire, and that's carbon that was stored in the rocks as opposed to coming out more recently to make plants. So the population itself doesn't drive CO2. It's actually the burning of fossil fuels by our population.
Jerry writes, and he wants to know, so when we drink carbonated beverages, what happens to the carbon we consume?
Well, I think mostly carbonated beverages, that stuff is not doing much in your gut, except probably making you burp. So it's a little bit impolite for me to say that, but most of that's just going to come right back out.
Okay, very, very good. Here's one. John was wondering how much CO2 is lost to space.
Virtually none of the CO2 is lost to space. The CO2, the only part of our atmosphere that is long-term lost to space is hydrogen, and the reason is that hydrogen is a light enough molecule that the molecules, if they're very hot, high temperature, high speed molecules, they can achieve escape velocity and actually be just sort of leaked out into space against gravity. But CO2 is a heavier molecule, and it is better retained by the gravity of the Earth, so there's virtually no loss of CO2 to space over time.
Vienta writes and wants to know what parts per million of CO2 is healthy for the atmosphere.
Well, I don't know about that. So there's about 400 parts per million of CO2 in the atmosphere right now. In the very distant geologic past, it's probably been 10 times that high. Of course, it was much, much, much warmer on the Earth at those times, you know, with dinosaurs in the Arctic and palm trees and stuff. It's also been maybe one half of what it is now in the past. At those times, it's been very, very cold in the atmosphere. At all of those times, there's been healthy life, but the CO2 has changed very, very slowly over time. It's taken millions of years for those changes to happen. So as long as you give it millions of years to change, I guess anything is healthy, because over millions of years of time, the life just sort of evolves to deal with it. The trouble now is we're changing it in 100 years, not a million years, so it's kind of hard for stuff to keep up.
Thanks. Janice writes in, has anyone thought of actively mixing the deep ocean water with upper ocean levels? Is there a way to do that? Boy,
well, that's a fascinating question. So yeah, as a matter of fact, we have thought about this. You couldn't do it globally, and you wouldn't want to. It takes an enormous amount of energy to mix the oceans, right? You take in buoyant water, and it's kind of like taking a basketball and trying to hold it down at the bottom of a swimming pool, right? It takes a tremendous amount of energy to take the buoyant water and stuff it down below the heavy water, the cold water at the bottom. Where are you going to get all the energy to do that? You know, I guess you'd need a giant source of energy, but you wouldn't want it to be burning coal. You'd want some sort of carbon-free energy. But if you had enough carbon-free energy to sink the water, well, that would be plenty to keep the lights on, so you might as well use it for that instead. Then you wouldn't have this problem. The other thing is the deep ocean actually has a tremendous amount of carbon in it. If you brought it up to the surface, it warmed up, it would go flat. It would degas like a warm beer, and you'd actually increase the total amount of CO2 in the atmosphere. It's a little counterintuitive, but not only couldn't you do it, but you wouldn't want to do it.
Okay, we're getting a lot of questions, and we'll take some more here. Ann writes in, is the dissolved CO2 making carbonic acid what causes acid rain? Is that where we get acid rain?
No, carbonic, I mean, there's a little bit of carbonic acid in the rain, but acid rain is worse than carbonic acid, worse than CO2 dissolved in the rain. Acid rain that's a problem for us is nitric acid and sulfuric acid that gets dissolved in the rain, much stronger acids than carbonic acid. And those come from, the sulfuric acid comes from burning high sulfur coal, and the nitric acid comes from industrial combustion that burns some nitrogen in the smokestacks or the internal combustion engines. And that nitric acid and sulfuric acid gets into the clouds and drips down as acid rain. It's kind of a different problem.
Okay, Carl writes, and he wants to know, did CO2 play a part in the Earth coming out of the last ice age, or was it something else?
Yeah, so that's a great question. The Earth came out of the last ice age, took about 10,000 years. The worst part of the ice age was 18,000 years ago, 16,000 BC, started to warm up. And as soon as it started to warm up, the CO2 started to go up too. And so they sort of happened together. It warmed up a little bit, the CO2 went up a little bit, it warmed up a little more, CO2 went up a little bit more. So the CO2 helped it warm up, but it started to warm up on its own, and then the CO2 sort of amplified the warming. It took 10,000 years for the CO2 to warm up the climate at the end of the ice age, so 100 centuries from 16,000 BC to about 6,000 BC. And over those 100 centuries, the world warmed up about 5 degrees Celsius, about 9 degrees Fahrenheit. So you can sort of imagine 1 degree Fahrenheit for each 1,000 years. Now we're talking about having that much warming, 5 degrees Celsius, 9 degrees Fahrenheit, over 1 century. So it's the same amount of warming as the end of the ice age, only 100 times as fast.
Okay, here's one from Leanna. Wants to know, is it possible that the ocean will warm such that water will no longer be able to sink at the poles, thus to change the circulation of the oceans, the ocean currents?
Yeah, that's one of the things that people are particularly worried about, and not everybody thinks that's actually stopping it completely is very unlikely, but it certainly could slow down, maybe by half, maybe by 3/4. And it depends on how much warming the surface ocean gets. Of course, the more warming you put in the surface ocean, the more it slows down the mixing with depth. and that slows down the uptake of CO2 from the atmosphere and makes it warmer. So that's one of the big concerns about the sink saturation. The overflow of those sinks depends on how warm you make the polar oceans.
Ronell wants to know, do you have a favorite way for carbon dioxide removal?
Favorite way? You mean to do it on purpose? Yeah, probably growing plants is the best way of all. It's been evolved by plants over billions of years. Of course, they've got to not die, right? So growing forests where there didn't used to be any forests, that's a good way to get rid of CO2. Forests that are already there, don't cut them down. But actually sucking CO2 out of the atmosphere to get it gone, similar to the mixing of the oceans problem, it takes energy, right? The reason that we burn carbon and break down those big molecules is because the energy gets released, and that's what drives civilization. To actually take dead CO2 out of the air and combine it into long-chain molecules, put it away, that uses energy. If we had enough energy to do that, we could use that energy to power civilization, and then we wouldn't have this problem to begin with. It's certainly cheaper to make energy without putting CO2 in the air than it is to just stick it in the air and then try to get it back out.
Well, Homer from Alabama writes in, he's got two questions. He says, do you have any data on volcanic emissions of CO2? And then the other one, the other question he had there was, is there any data on non-fluorocarbon fuels such as wood burning, etc.?
Yeah, sure. So the volcano thing, in the long run, that's where all the CO2 comes from, is basically degassing out of the solid earth through volcanoes. That's where the CO2 originates from over geologic time. The rate of emission by volcanoes is about 300 times less than the fossil fuel emissions. So really just a rounding error in the fossil fuels. It's tiny, tiny compared to the amount that we burn with coal, oil, and gas, about 300 times less. And with regard to burning wood and dung and all that kind of stuff, that's a source of CO2, perhaps 10% of the amount that we get from fossil fuel. But on the other hand, all of that carbon was recently CO2 in the atmosphere, right? The plants made that wood by photosynthesizing, so it came out of the atmosphere, then we set it on fire, it goes back into the atmosphere, so there's no net change of carbon in the atmosphere by burning firewood. The only net change is if you dig the carbon out of the millions of years old fossil reservoirs and then set that on fire.
Okay, Michael wants to know, if he understands your presentation, we should be letting more forests grow and die out on their own to begin rebalancing the CO2 levels. Do we have enough vegetative space left on the planet to make this feasible?
Well, he's exactly right. Except just growing them and letting them die, that doesn't change the carbon. You have to grow them and leave them alive, right? The rate, you have to have more forest when you're done than you did when you started, and that's really the root of his question. And the answer is no, there's not enough. There's enough room on the earth to grow forests where there didn't used to be forests. So you could get rid of, maybe 10% of the fossil fuel emissions by growing forests where forests can grow, but there's not already forests. Like, you can't do this in the Sahara because there's not enough water. Doing it in the Amazon doesn't get you anywhere because there's already forest there. You have to grow forests where forests could grow, but there aren't already forests. And unfortunately, we're already using most of that land to grow food, right? So you got kind of this trade-off. I could get a 10% CO2 fossil fuel reduction if I took all that nice land out of food production and put it into growing woods. But really the answer, this might help a little bit, but the real answer is you got to stop setting carbon on fire.
Okay, Eva writes in, she said a recent news report commented on a very large sinkhole in Siberia that is widening. Is the widening chasm related to the burning of fossil fuels? I'm not sure.
Maybe. Nobody really knows for sure. It could certainly be that those sinkholes that are forming around Siberia and Canada have to do with thawing the permafrost, and when it thaws it kind of collapses on itself, and that's from warming, which is from CO2. But nobody's really completely sure about that.
Okay, Diane wants to know, does carbon affect the magnetic field that protects the Earth?
Not that I know of. Magnetic field is generated by the metallic core in the center of the Earth that's, rotating iron. There's not, to my knowledge, any interaction between that. That's happening thousands of miles below our feet. Difficult to imagine how that's related to CO2.
Mary wants to know if you can speak to the trading of carbon credits on the Board of Trade from 2007 to 2010.
Well, there's all kinds of these carbon markets. There's been one in Europe for 20 years. There's been this, I think she's talking about this Chicago Mercantile that does carbon trading since '07. The whole idea is, of course, you can sell the carbon that you didn't emit to somebody else who can take it as a credit. The whole idea is making carbon worth money and allowing the free market to help us to reduce our emissions. Certainly economists think using market mechanisms like that is the best way to reduce our emissions. Kind of not my field, but sounds like a good idea to me.
Mary writes in, if today's carbon output will have effect for centuries, is there any motivation for most people or most to reduce carbon output?
Yeah, I would actually say that gives us more motivation. It's centuries, even millennia. I mean, thousands of years, because every bit of emissions that we don't make today, like if I drive a Prius instead of an SUV, or if I turn down my thermostat a few degrees, will help people for 100 generations, right? This isn't just me, and it's not just my kids or grandkids. It's everybody down the line for thousands of years.
Now, Jerry wrote in about the drinking carbonated beverages before. He follows up with, do carbonated beverages ultimately contribute to and increase atmospheric carbon?
Only if the carbon in carbonated beverages comes from fossil fuels. So remember, the growth equals death in the long run. All things must die. So if you're making carbonated beverages from yeast and beer or something like that, or wine, then that is atmospheric carbon that's just going right back out. Doesn't do anything to the total amount of CO2. But if you're digging coal and burning the coal and then taking the CO2 from the burnt coal and then making, Coca-Cola or Budweiser out of it, then yeah, that's adding to the CO2.
Okay, here are two kind of related questions, one from Thomas, one from Robert. Do you foresee the continuing rise of average global temperature as a linear function, or something more dramatic, assuming fossil fuel goes on unabated? And then the question there by Robert was, are there more weather extremes in the past 150 years? Is there reliable evidence to demonstrate these trends?
So, wow, first one about does CO2 increase steadily, linearly? It really is a linear fraction of the fossil fuel. So the easy number to remember is half of the fossil fuel carbon goes into the air, because half of it doesn't. So fossil fuel emissions times 0.5, that's equal to the rate of increase of CO2 in the atmosphere. And that has not been linear in the past because we've been burning CO2 or burning fuels faster and faster. That's basically just economic growth. If people get off of fossil fuel and onto nuclear and solar and wind and hydro, then that rate will decrease. On the other hand, if China and India and Africa wind up building modern economies based on coal, that rate of CO2 emissions will increase. So whether it's linear or exponential or it drops off, that's really up to people, up to everybody. It's not an Earth system thing. That's a policy thing. With regard to extreme weather, that's probably another webinar, right? The relationship of extreme weather. I would say heat extremes, almost certainly related to CO2. Intense rainfall, just because evaporating more water from the oceans gives you more water to rain from, that's probably related. But other things like hurricanes and tornadoes and hailstorms, probably not. So it really kind of depends what kind of extreme weather you're talking about.
Bill has a question for your opinion. Do you feel we should put a fee on carbon fuels to reduce the incentive to use them and stimulate the development of carbonless energy technologies?
Well, you're asking my personal opinion here because I'm a scientist, not an economist. But certainly that's what economists think. They think that the way that you drive innovation in free markets is to make it worth somebody's while to innovate, right? So if you make it worth money for people to invent low carbon technology, by golly, they go out and invent low carbon technology. So there's almost nothing better in a free market than rewarding people for doing the stuff you want or discouraging them from doing the stuff you don't want.
Tommy from Virginia, this is an interesting question, would like to know if we could, is there a way to start lightning rod farms as storage devices? And I guess
for electricity? Storing lightning. Wow, I hadn't thought of that one.
Clean Energy thought that would be a way to have a bunch of lightning rod farms, and we could store that. So
yeah, get Elon Musk to build some sort of giant battery that's connected to the lightning rods and suck up all that juice that's flowing from the atmosphere and then run our houses off the batteries. What a brilliant idea! I honestly don't know if such a thing could be possible, but boy, if so, that'd be awesome.
Yeah, I guess you'd need it more in the tropics where there's more lightning. You would want to have that on the West Coast somewhere or something.
Yeah, I guess so.
Hey, how we do? You doing okay on time? We have some more questions, or
I'm happy to go as long as you like, but I know that we're sort of out of time. It's up to you.
Yeah, let's go about 5 more minutes, and then those that we don't get to, if you wouldn't mind following up with folks, that would be
delighted to follow up on email.
Hey, George wants to know, what about carbon and methane?
Yeah, so methane is an even better greenhouse gas than CO2 because it's got 4 bonds to wiggle. It's CH4 instead of CO2. So instead of just 2 bonds, there's 4 bonds, and each one of those wiggly bonds can absorb and emit photons, something like 85 times as powerful of a greenhouse gas as CO2, but there's 200 times less methane in the atmosphere than there is CO2. So it contributes to global warming, but not nearly as much as CO2. The other thing about methane is that it is chemically reactive, where CO2 is not chemically reactive. So you can put CO2 in the air and it just piles up and stays up there for many centuries. Methane reacts with oxygen in the atmosphere to break it down. Has an atmospheric lifetime of about 12 years compared to many centuries for CO2. So for a little while, you make methane and it winds up being a huge greenhouse gas. On the other hand, it doesn't last very long in the atmosphere. So over the long haul, CO2 is really the only game in town, but over a period of a decade or two, the methane that you put in the atmosphere also contributes to global warming.
Okay, we're going to take 2 more questions as we wind things up. George writes in and he says, how do we as physical scientists get this information and the associated ramifications out to the public as a whole?
Well, I suppose CoCoRaHS webinars are one way to do it.
That's a great idea. Yeah.
I've spent the last 2 years doing a whole bunch of trainings and classes for TV weather forecasters in a bunch of different cities through the American Meteorological Society and the National Weather Association. So you know, weather forecasters talk to millions and millions of people every single day, and they're maybe the scientist that is best known in everybody's living room. So I also teach classes, and there's websites, and you can tell your friends, you can download my slides, you can read this article that's linked on your screen there. I don't know, we try to do it the best we can.
Okay, here's the last question of the day. Gail writes in and wants to know, how will weather change by the expansion of the forest northward if it takes over tundra regions?
Yeah, well, that's a fascinating question. Certainly as you grow dark trees over what used to be just snowy tundra, that makes the surface darker, makes it soak up more sunlight. It's called that a lower albedo, and that probably drives an even warmer Arctic. The other thing, as I mentioned, is that if you keep warming the Arctic, you wind up not just growing trees and sucking up CO2, but you probably also thaw the permafrost. It turns out there's almost twice as much carbon in permafrost as there is in the atmosphere. So, you know, we have about 400 ppm of CO2 in the atmosphere. There's probably another 800 ppm just in the permafrost. If we were to thaw that out and let the carbon decompose, it's like taking, you know, turning off your fridge. All the meat in your freezer is going to rot. And similarly, if we warm up the Arctic, all that carbon that's frozen in the permafrost is going to rot, come back out. So probably a really big problem in the long run. We got to be sure we stop putting CO2 in the atmosphere before all that happens.
Well, Scott, again, fascinating webinar. We really appreciate it. In fact, maybe I'll stop by with a carbonated beverage we can share. There we go.
Thank you very much, Henry. It's been delightful talking with you.
We really appreciate it. Well, folks, mark your calendars and please join us for our next webinar. And that's coming up on Thursday, May 11th. So not too long from now. Keith Sider, very fortunate to get Keith. He's the director of the American Meteorological Society, and he will tell us all about the society. You may have questions about who they are, their history, what they do, how you can become involved. It's a great organization, and we'll have more information on that. So we'll hope you'll join us again on Thursday, May 11th. We'll have the registration up there in a couple weeks for that. Finally, when you sign off today, again, please take that survey. It's going to pop up on your screen, and so appreciate you doing that. So, folks, until the month of May, this is Henry Regis for the rest of the CoCoRaHS headquarters team. We're going to say so long for now, and we're going to wish you a great week ahead. Thanks for being part of the webinar today. Take care.